Welcome to Chapter 20, Section 3. We are going to be talking about transformers. And no, not the movie kind. This is our last section, our last video of the year. So what we're going to do, this part here is from 20.2. Okay, we're going to describe how mutual inductance occurs in circuits, and we'll learn what that even means. And then we're going to apply our transformer equation to solve problems involving step-up and step-down transformers. So what is mutual inductance? Okay, so if we take an iron ring, so that's what this is, an iron ring, and we wrap a coil of wire around one side. Okay, so here we've wrapped wire around. Okay, and when we put current through it, right, we induce a magnetic field. So that's what this green line here is. That is our magnetic field. Then, if we take a second coil of wire and wrap it around the other side, then this magnetic field induces a current in this wire. Okay, so this is mutual inductance because the process goes from current, right, inducing a magnetic field, and then that magnetic field induces a current in the other side. So we go from current to magnetic field to current. One of the key things to remember here is that when we do this one, right, the magnetic field needs to be changing or the wire needs to be moving, okay? So what that means is this magnetic field, because we can't really move this wire in relation to this field, okay, this magnetic field needs to be changing, okay? So this B field here needs to be changing. So we're going to have to use AC current in order to generate it, because AC is always changing. So when you're changing this coil of wires current all the time, you're going to be constantly changing this magnetic field. And this magnetic field changing will induce a current here, which will then also be AC current. So the things that we need, okay, these are the requirements. We need a soft iron core. Okay, it can't be a hard iron core, which means its magnetic field can change. Okay. So we have a changeable magnetic field. We need wire coiled around the core at two separate places. Okay, and like I was explaining the last slide, we must have an AC source. So these are our requirements, okay? Requirements, there we go. So why do we have transformers? What is their purpose, okay? Well, transformers allow us to change the EMF, right? Remember, EMF means voltage, okay? And we may need a higher or lower EMF than we have a source for. So what we have might create maybe 10 volts, but what we need is 100. Or maybe it's the other way around. Okay. Also, changing the EMF can affect the power and reduce the energy lost in wires as we transmit electricity long distances. Okay. So as they go over these transmission wires. And we'll take a little look at that closer later. So there are two types of transformers. Okay. We can have a step-up transformer, which has a secondary EMF or voltage greater than the first. And we can have a step-down transformer that does the opposite, and its secondary EMF is lesser than the first. And the way that we do this is we determine whether it's step-up or step-down by the number of windings, okay? So a winding this way here, this word here means each coil of wire is one winding. So there's 1, 2, 3, 4, and so on. Okay, each of those loops is a winding. Okay, and then from that we can use the transformer equation also to decide if it's step up or step down. So what is the transformer equation? Well, this is it here. It tells us that the voltage that we get over here, okay, and when it says V2, that would be the one you get out of this side. So this is our EMF2, and this is our EMF1. Okay, which means that the number of windings here, okay, we can count all of these. And if we did count them all, we would find that there's 16 windings. So this would be our N1, and that's going to equal 16. Now, if we count these other ones here, it's really easy, and we could do it just now. We can see that there's 7. So that means our N2 here is going to be 7. So we can then use this to figure out how the voltage will change from one to the other. Okay, so let's just do that real fast. Let's say we start out with delta V1, okay, equal to 100 volts. Okay. Now our windings are lesser, so in this case, this is a step-down transformer. Okay. And step-down means that our voltage will decrease. Okay, so our secondary voltage should be less than our primary voltage. That doesn't look like a 2 very much, does it? Okay, so let's see if that works. We're going to plug things into our equation here. Okay, so we're going to find out what delta V2 is. Okay, so we're going to need N2, which is 7, divided by N1, which is 16, times delta V1, which is 100 volts. So I have 7/16 times 100, so our delta V2, or our secondary voltage, will be 43.75 volts. Okay, so it is indeed less than the 100. Okay, so this is how we use this transformer equation and how we identify whether it's step up or step down. So this might seem kind of like something for nothing, okay? It's almost magical, right? We can take 10 volts, we can turn it into 100 or 1,000. We just need to change the number of turns of wire. But really, the power output is still conserved. So as V increases, current will decrease. Okay, so notice that. If the output here for power is conserved, what that means is P1 will equal P2. So if we look at our last one where we went from 100 volts down to 44 volts, okay, it was 43.75, that means the current here, okay, this current 2, okay, this must be greater than the current 1. Okay, it must be bigger, so that we end up with I1 V1 will equal I2 V2. Okay. Also, some energy is always lost to heat because of resistance. Okay, so that means that this equation that we use, that transformer equation, tells us at the very best we could get these 44 volts out of it. But the reality is, because we're losing some energy to resistance, it might actually be like 43 or 42. Okay. So the transformer equation assumes no power is lost, but in reality we don't get 100% conversion. Okay, the secondary coil in reality will always have less or lower EMF than what you can calculate. Okay. With that, okay, most typically have an efficiency of 90 to 90%. So we calculated 43.75 volts, right, which we can round to 44 volts. Okay, if, say, it's 90%, okay, then what we would actually get would only be about 40 volts out of it instead of 44. Okay, so we do lose some energy. Also, the power lost in transmission lines, which is the wires that carry all your electricity to your house, is lost according to the equation P equals I squared. This should be a squared R. So transformers used to create high EMF and low currents, okay, to reduce the power lost in transmission. Okay, so they increase the voltage, okay, so that it decreases the current while being transmitted. Okay, and then that will return it to normal at your house. Alright, so that brings us to the very end of chapter 20 in our last video for the year. I will see you guys in class, and let me know if you have any questions there.